Hi everybody, welcome back. So as you can see, we are going to continue with our review of chemistry in the Barens book. This is the high school version of the Regents is what we're doing. I also wanted to tell people you definitely need to subscribe if you're going to pursue any health careers, nursing, medicine, or something scientific, right? We're going to be doing chemistry for a little while. I'm Nicolette. I'm a tutor from Gab-Nic Excelsior Nursing Tutoring Center. We're actually going to go 30 minutes this time around. So let us go straight into it. And also, if you are a nurse or and want to ensure that you or you've graduated as a nurse and you want to take your NCLEX or you want to do some review, I do have classes on Thinkific in under Gab-Nic Excelsior Nursing Tutoring Center. I'll put descriptions below so you can see where you can get those review classes. Okay, so let us continue with our review in chemistry. We are up to page number 6 if you have bought the book and you want to read along. So let us commence. So separation of mixtures. One way of distinguishing between mixtures and substances involves the ability to separate mixtures by physical methods. For example, it is possible to separate a sand-water mixture by allowing the water to evaporate. When a physical method is used to separate a mixture, the chemical properties of the mixture's components are not changed. We discuss these separation techniques below. The first one is filtration. Suppose you have a sand-salt mixture, and we want to separate the sand from the salt. The technique known as filtration will accomplish the task of recovering the sand. Oh, I again forgot to start my clock. 30 minutes. Suppose we have a sand-salt mixture, and we want to separate the sand from the salt. The technique known as filtration will accomplish the task of recovering the sand from the mixture. First, we add water to the mixture, a procedure that dissolves the salt, but not the sand. Second, we find a funnel with a cone of filter paper and carefully pour the well-stirred mixture into the funnel, as shown in the accompanying diagram. Here is the diagram. So you see the funnel here, the beaker here. This is the mixture that they put water in to melt or dissolve the salt, so that once they pour it in, the sand will remain here and the salt water will go in there. Okay, so the salt water solution that passes through the filter paper into the beaker below is known as the filtrate. The sand remains on the filter paper. To remove the last traces of salt from the moist sand, we wash the sand several times with pure water. We then allow the sand to dry, either in air or in a heated oven. Next is evaporation. The next step is to recover the salt from the salt water solution. Drying would work, but would take a very long time. In situations such as this, we use the technique known as evaporation. We pour the solution carefully into an evaporating dish and cover the dish with a watch glass. Then we heat the entire assembly gently over a low flame until the water boils and is completely evaporated. The watch glass prevents the salt from spattering during the heating process. The accompanying diagram illustrates this technique. So here you have the picture they're referring to. The solution is in there. That's the glass here. That's the Bunsen burner with the fire that's heating it up slowly. In the event that strong heat is required, a crucible is used. Crucibles are frequently made of porcelain and are supported by a pipe stem triangle while being heated. The accompanying diagram illustrates the use of a crucible. So this is the crucible. So this is the porcelain, and then you have the triangle thing right here. That's the fire right there. Next one is crystallization. Yet another technique we can use to separate a dissolved solid from its solvent is known as crystallization. In this technique, we prepare a concentrated solution at a relatively high temperature and allow the solution to cool slowly. As it cools, solid crystals form at the bottom of the vessel containing the solution. Let's read that again. Yet another technique we can use to separate a dissolved solid from its solvent is called a crystallization. So separating a solid from its solvent. So the solid obviously is like the salt, right? And the solvent would be the water. In this technique, we prepare a concentrated solution at a relatively high temperature and allow the solution to cool slowly. As it cools, solid crystals form at the bottom of the vessel containing the solution. At times, the solution becomes supersaturated and the crystals do not form immediately. In this case, we can initiate crystallization by adding a single seed crystal of the solid to the solution. This concept, for some reason, is not very clear for me, and it wasn't clear at all until I looked it up on YouTube. So if you're like me and you're not truly grasping the information, so you have this solution that is super saturated because there's a lot of the salt in the water, right? So there's a lot of it. So now it's heated up to boiling temperature, right? And then they allow it to cool slowly, right? And then they said the crystals will form in the bottom. And so if it's not happening fast enough, they put a crystal seed, they drop it in there, and that initiates the crystallization. So when I looked on YouTube at crystallization, I did see them like they dropped this little droplet of fluid, and then it was like this white spiky crystals started to form and until it took up the whole beaker of solution. So if you want to be able to see it better, I'm a visual person, so definitely go look at that YouTube video of crystallization. Let's move on. Distillation. Suppose we have an aqueous solution containing dissolved solids, but it is the solvent that we want to recover. In this instance, we use the technique known as distillation. So you have a dissolved solid, right? So you have the salt that's dissolved in the water, but you want the solvent to be recovered. So you want the water to be recovered and not the thing that's melting, the salt. We place the solution in a boiling flask and heat it to boiling. As the solvent vapor passes out of the flask, it passes through the condenser, right? So you'll have the salts are boiling, they're melting, so they haven't melted yet, right? But the water is boiling, so it'll start evaporating. And so then whatever is evaporating is not the salt, right? Because the salt would have remained in the bottom, right? Because when we wanted to get only the salt and not the solvent, we let it evaporate and the water left and the salt remained. So now if you have the salt and the water together and you want to get only the water, you know that the salt is going to remain in the bottom. So whatever is going to be evaporating is the solvent. If you want to separate it, that's how it's going to happen, right? But then it says, as a solvent vapor passes out of the flask, it passes through a condenser, a tube that is surrounded by an outer tube containing cold water. The cold water condenses the vapor in the tube and the solvent is collected in a second flask. The collected solvent is known as the distillate. The accompanying diagram illustrates one way of distilling a solution. So you know that heat causes vapor, and when you cool it, it'll come back into liquid. And so that's why once it comes out, right, here's the diagram. So you have this one here is being boiled. This, the heat is boiling. The little dots are the salts, let's say, right? And so then as they're boiling, as they're melting, right? They haven't melted yet, but the water starts boiling. The water is evaporating and the salts are going to remain at the bottom, right? And so now as the vapor is coming up, it's going to travel through this tube. And so you see that there's this white thing in the middle. That's where the vapor is. So all around it is cool water that's going to condense it. That's going to make it, so this caused it to vaporize, and that was hot. So if this is cold, it's going to cause it to go back to the condition that it was before, right? And then this is what's collecting it all. So in the end, you'll have the water here and the solute, the particles here. Moving on. There are a number of other types of distillation. In chapter 11, we will learn the process of fractional distillation. We will learn that the process of fractional distillation is used to separate petroleum into simpler mixtures of liquid carbohydrates or hydrocarbons, and that this process is dependent on the differences in the boiling points of the hydrocarbon fractions. Next, we're going into the chromatography. So another technique used by chemists to separate mixtures is chromatography. So at this point, if you had not looked up the word chromatography, you would find the word here. But in my learning techniques, I find that you will not always have the definition of the words that you don't understand show up later on. So it's always wise that you look up the word that you don't understand. And then thankfully, if it does show up, you kind of have a little grasp of what it is already. And this is like a reinforcing or a better understanding of what the word meant. So the word chromatography comes from the Greek word chroma, color, and graphene, to write. The term was coined by the Russian botanist Mikhail Suvet, who used the technique in 1906 to separate a mixture of plant pigments. In chromatography, a spot of a mixture is placed on a stationary phase, such as paper. The stationary phase is then placed in a sealed container of solvent, which is known as the moving phase. As the solvent moves along the stationary phase, it carries the mixture with it. If different components of the mixture have different degrees of attraction for the stationary phase, they will travel at different speeds along it and will be separated from one another. The accompanying diagrams illustrate how one technique, known as the ascending paper chromatography, is used to separate the components of a mixture. Okay, so here's the diagram here. So you have the solvent here. This is the solution. It's called the solvent front, right? So whatever the liquid's here is going to be kind of like saturating this, and it's going to move up. And then this is the dot of whatever mixture you want to see what's in there, right? Compared to what's in this. If they interact as they meet, and they'll travel up. So you'll see how they travel up. And here is an example, right? So this is where the dot was. It traveled and it separated because there were different particles in it, and they reacted differently to the solvent. Guys, I have allergies, and sometimes my nose is so itchy. I apologize for scratching my nose so often. Okay, so it says an element cannot be separated, and a compound can be separated only by more drastic chemical methods. These methods will change the chemical properties of the components and are part of the compound. For example, when the compound water is separated by using an electric current, this familiar liquid is replaced by two gaseous elements, hydrogen and oxygen. The chemical properties of these elements are very different than those of water. The accompanying diagram presents a scheme for distinguishing among the various types of matter. So here is the scheme, right? So you have right here, which is matter. Right here it says, can it be separated by physical methods? If it is no, this is no, then it's a pure substance. If it's a pure substance, then you have to ask, can it be separated by chemical methods. So if it's no here, then it's an element, because elements are the last resort, right? But if it's yes, then it's a compound, because compounds are pure as well because they're fixed, but there are different elements in them. So you can separate the elements by chemical methods. So on this side here, the matter, when we had asked the question, can it be separated by physical methods? If it's yes, then it's a mixture. So now, if it's a mixture, it can either be, then the question is it uniform? If it's no, it's a heterogeneous mixture. And if it's yes, it's a homogeneous mixture. Okay, so moving on. Now we're going to talk about energy. So energy, it is not easy to define energy precisely, but we are all familiar with at least some of its forms: thermal heat, chemical, electrical, electromagnetic radiation, which is the same as light, nuclear, and mechanical energy. Mechanical energy is divided into kinetic energy, the energy associated with motion, and potential energy, the energy associated with position. As students of chemistry, we will be particularly interested in heat and in mechanical and electrical energy. All forms of energy are associated with the concept of mechanical work. These associates, which associates a force, so let's start over. All forms of energy are associated with the concept of mechanical work, which associates a force with a change of position. So all forms of energy are associated with the concept of mechanical work. So all energy involves physical, mechanical, actual work, because there's a change in position from where it was to where it's going, okay, or where it ends up. For example, we use a vacuum cleaner to transform electrical energy into the mechanical work needed to lift and remove dirt from a carpet. So it's moving the dirt from one place to the next. The concept of energy is of great importance in chemistry. For example, chemical reactions may absorb energy, endothermic reactions, or release energy, exothermic reactions. Many reactions involve the conversion of one form of energy to another. So that's moving from endothermic to exothermic, or exothermic to endothermic. Yet, as a result of countless experiments, chemists have arrived at the conclusion that energy is never destroyed in a chemical change. Rather, it is conserved. The role of energy in chemical reactions will be treated more fully in Chapter 5. Although work and energy may seem very different, they are closely related. In fact, the same unit is used to measure both quantities. So work and energy are super close, right? And they use the same unit. In the SI, as shown in the first paragraph, this unit is the joule. That's Joule, or abbreviated capital J. Its multiple is the kilojoule. That's small k, capital J. An older method of measuring energy involves calculating how much heat energy is absorbed or released by a substance. This older unit of energy is the calorie, CAL. Its multiple is the kilocalorie, KCAL. Originally, the calorie was defined as the amount of heat energy needed to change the temperature of 1 gram of liquid water by 1 Celsius degree. The calorie is now defined in terms of the joule. 1 calorie equals 4.2 joules. That is something I think you should memorize. 1 calorie equals 4.2 joules. Section 1.3, measurement and the metric system. The basis of all science lies in the ability to measure quantities. For example, we can easily measure the length or mass of this book if we have some standardized system of measurement. We use the Système International, SI, and its derivatives because scientists all over the world express measurements in metric units. The SI has established 7 fundamental quantities upon which all measurement is based. Number 1, length. Number 2, mass. Number 3, temperature. Number 4, time. Number 5, number of particles. Number 6, electric current. And number 7, luminous intensity. For each of these quantities, there is a unit of measure based on a standard that can be duplicated easily and does not vary appreciably. Let's first see length. The unit of length is the meter, which is approximately 39 inches. In chemistry, we also use various subdivisions of the meter. Picometer, PM, that's 10 to the negative 12 meters. Nanometer, NM, 10 to the negative 9 meters. Millimeter, MM, 0.01 meters. Centimeter, CM, 0.01 meters. Decimeter and decimeter, DM, 0.1 meter. The prefix pico, nano, centi, and so on are known as metric prefixes. A list of these prefixes appear in section 1.4. Let's see. Section 1.4, so that's this one here. So you have a list of all of them. Can we focus? Probably not. Okay. Then we have mass. The unit of mass is the kilogram, which has an approximate weight on Earth of 2.2 pounds. I think that's something else we should memorize. We note that mass and weight are not the same quantity. Keep that in mind. Mass is the amount of matter in an object contained. So mm. Mass is the amount of matter, while weight is the force with which gravity attracts matter. In chemistry, we also use the gram. So just quickly, so mass is the actual, what it is, what the matter is, right? So mass is the amount of matter an object contains. So what does it measure in how much there is, or how much is existing in my hand? But then weight is how gravity interacts with the amount in my hand, right? So in chemistry, we also use the gram, which is 1,000 grams equals 1 kilogram, as a unit of mass. The next measurement is temperature. Temperature measures the hotness of an object. The SI unit of temperature is the Kelvin, capital K. The fixed points on the Kelvin scale of temperature are the 0 point. 0K, known as absolute zero. That's something to know. 0K, known as absolute zero. And 273.16 kilokelvin, which is known as the triple point of water. So 273.16 K is the triple point of water. More will be said about the Kelvin scale of temperature in chapter 6. So what I was reading this, so just so you know, this is my second time reading this. So when I read it, when I came upon triple point, I was curious as to what it is. So in the course of my studying, I've been studying for this MCAT for, it's been since I think 2 months now. So I've read the MCAT book already. I've watched 2 YouTube full videos, well, one full and one halfway, and then I picked this book up. So I was aware of triple point and I couldn't remember what it was. So then I went and I looked it up again. And so the triple point is 3 matter phase. This is where 3 matter phases exist. So this is where the gas, liquid, and solid phase meet at that point. That is a triple point. Just so you know. Again, like I said, whenever you come across a word that you do not understand, you should stop and look it up because it will help you as you go on. So again, the fixed point on the Kelvin scale of temperature are the 0 point, which is 0 Kelvin, known as absolute zero, and 273.16 Kelvin, which is known as the triple point of water. More will be said about the Kelvin scale of temperature in chapter 6. In chemistry, we also use the Celsius temperature scale, 0 Celsius. Originally, the fixed points on this scale are set at the normal freezing and boiling points of water, 0 degrees Celsius and 100 degrees Celsius respectively. Again, in chemistry, we also use the Celsius temperature scale. That's the little Celsius sign, degree in Celsius. Originally, the fixed point on this scale were set at the normal freezing and boiling point of water, 0 degrees Celsius and 100 degrees Celsius respectively. So the normal freezing point was 0 degrees Celsius and the boiling point was 100 degrees Celsius. We can convert between Celsius and Kelvin scales using the simplified equation that appears in reference table T in Appendix 1. But they gave us a sample. It's K. So it's K equals degrees Celsius plus 273, right? That is how you convert Celsius to Kelvin and Kelvin to Celsius. Our next measuring method is time. The unit of time is the second, little s. In chemistry, we also use the familiar minute, min, or hour, little h, day, little d, and year, little y, as units of time. And I do mention everything, right? I read off everything, but it's important that you know these symbols, because as you write your equation and you work through your problems, you're going to have to kind of cancel out the different abbreviations and whatever, because that's important. And then you'll know if your formula was accurate, if your problem solving was done correctly. Number of particles, that's our next measurement. The unit of number of particles is the mole, MOL. The mole is a very large number, 6.02 times 10 to the 23rd. So the mole, so 1 mole is 6.02 times 10 to the 23rd. That is a number that you must memorize. Thankfully, I have memorized it already. And you know, something that I do is when it comes to mind as I study, I always go back to feed my brain what it wants. So being that I'm saying to memorize this and I have this memorized, the image of 2.2 came to my mind. And I remember that I had to memorize that too. And 2.2, it's 2.2 pounds, right? And so it was 2.2 pounds is the weight. So the unit of mass is a kilogram, which has an approximate weight of 2.2 pounds. So 1 kilogram is 2.2 pounds, right? And we also wanted to memorize that 273.16 is the triple point. I also said to memorize 1 calorie is 4.2 joules, right? So anytime that you find something new to memorize, you should always go back and review the other things that you memorized so that they're not replaced. Because the thing about our brain is that it makes room for more information, right? So we don't want to forget our old information because we're putting in new information, right? And remember that K equals C, which is Celsius plus 273. Moving on. So the unit number of particles is the mole. The mole is a very large number, 6.02 times 10 to the 23rd. In chemistry, we frequently need to know the number of particles, such as atoms or molecules, in a sample of matter in order to predict its behavior. The next measurement is electric current. The unit of electric current is the ampere, which is capital A. Electric current measures the flow of electric charge. In the SI unit of measurement, electric charge is a derived quantity that is based on electric current and time. The SI unit of electric charge is the coulomb. So we see that this is a little ambiguous here. So the unit of electric current, is the ampere, right? But the electric charge, so the unit of electric current is measured is in amperes, capital A. But electric charge is measured in coulombs, right? So the SI unit for electric charge is coulombs, but the unit for electric current is capital A. So that is something that you have to decipher. What the difference between electric current and electric charge, okay? So when we are exposed to those different words, we'll see and understand. And this is something that you should go ahead and look to see what's the difference when someone says electric current and when someone says electric charge, right? Moving on, and this is the last thing we're gonna cover. So luminous intensity, the unit of luminous intensity is the candela, CD. As its name implies, luminous intensity measures the brightness of light. We will not need to use this unit in our study of chemistry, and we're going to stop here. It's been 30 minutes. I hope that you were able to go through all of this section, understand it, and I will see you next time as we continue chapter 1 of our Regents Review of Chemistry. See you next time. Bye.